Alright guys, let's do this problem that says the member is supported by a pin at A and a cable BC. Determine the components of reaction at the supports if the cylinder has a mass of 40 kilograms. So first let's draw the free body diagram. I know that I have the weight right here, and that weight is equal to 40 times 9.81, which comes out to be 392.4 newtons. We have this tension right here, let's call it tension T. Then we have the reactions at A, which is a reaction in the positive C, a reaction towards a positive C, a reaction towards a positive Y, and a reaction towards a positive X. And then notice that this problem didn't say that the support doesn't also generate reactions for the moment, so we also got to draw those. And if you notice, just by looking at the rod, you can tell that there is a moment reaction about A, so it's stopping the whole system from turning. That's what it's doing. And then let me just keep here on the Z-axis, and it also has a reaction at C. Now notice that I always do the reactions, or just to follow some convention, that counterclockwise, as if you were looking at it from the positive axis, is positive. So if I was looking from the positive C, it would be counterclockwise would be the way I drew it. And if I was looking from the positive X, then counterclockwise would be the way I drew it. Now also notice that just by looking at the assembly, you know that there is no, it doesn't stop it from turning about the Y-axis. If you wanted to turn about the Y-axis, it would turn freely because of how it's attached at point A. So now that we have our free body diagram, we can start. First, I always tell you to the sum of the forces, right? About the X, the Y, and the Z. But in order to do so, we need to figure out the Cartesian vector form of T. So the Cartesian vector form of T is equal to a univector going from A to B times the magnitude of T. The univector from, oh sorry, that's not A to B, that's C to B. The univector going from C to B is equal to vector CV over the magnitude of vector CV, which is minus 3 in the I, minus 1.5 in the J, plus 1 in the K, all over the magnitude of that vector, which is 3 squared plus 1.5 squared plus 1 squared, all square rooted, and that would be 3.5. That being said, you get a univector, and in that univector you get T. The univector is minus 0.8571 times T. Well, that's not the univector, that's the whole vector already. Minus 0.4286 times T in the J, plus 0.2857 T in the K. The univector, I'm just gonna write it here so I don't get a lot of haters like sometimes I do when I skip steps. 571 in the I, minus 0.4286 in the J, plus 0.2857 in the K. And then you multiply that univector times T, and you get basically the Cartesian vector form of T. Now this allows you to do the sum of the forces in the X and the Y and the Z. So let's do it. In the X we have minus 0.8571 T plus AX is equal to 0. In the Y we have minus 0.4286 T plus AY is equal to 0. And in the Z axis, Z direction, we get 0.2857 T plus AC minus the weight, which is 392.4 is equal to 0. So we have 4 variables, but we only have 3 equations. That means that we're gonna need to do some a little bit of moment equations. That way we can get a couple of more equations and be able to solve this system. The thing is, when we do the moment equations, you're going to notice that we're introducing more variables, but bear with me, we'll figure it out. So the first thing that we're going to do is sum of the moments about the x is equal to 0. Now, if I was looking from the positive x-axis towards the origin, and assuming counterclockwise is positive, then I would get that the moment of ax plus the moment being generated by the weight, which is 392.4 times 1, because the distance from x, from here to here, is 1, plus 0.2857t. Why 0.2857t? Because that is the k component, that is the, let me actually draw. This is the c component of t, this is the x component of t, and this is the y component of t. Now, the x component and the y component of t are not generating any moment. Why? Because the y component is going towards the x-axis, so it doesn't generate a moment, and then the x component is parallel to the axis, it also doesn't generate any moment. But the other one is actually trying to turn it, so it's 0.2857t times 1. So we have a new equation, but we also have a new variable. So now we have 4 equations. Sorry about that. I got 4 equations, but 5 variables. So still not quite there yet. So let's do sum of the moments in the y is equal to 0, and this is the one that's going to save me, because in the y I noticed that what's generating a moment in the y. First I got the weight of the system, the weight of the cylinder, which is 392.4 times 3, because that's the distance from point D all the way to y. And then I have the 0.2857. Again, this is the c component of t. It's also generating a moment, which is 0.2857t, and it's negative because it's trying to turn it clockwise, times 3, which is the distance between c and the y-axis. And remember, I'm always assuming that counterclockwise is positive, as if I was looking from the top of the y-axis. And this is all equal to 0. And look, I only have one variable here, which is t, and I have nothing else. So this equation already allows me to solve for t, which is 1373.5 newtons. Awesome. Now I'm gonna call this, I'm gonna label my equations. I'm gonna call this equation 1, equation 2, equation 3. This is equation 4, and this is equation 5. So now all we gotta do is just some little math magic. Look, we plug in equation 5 into equation 1, and we get that ax is equal to 1177.2 newtons. We plug in 5 into 2, and we get that ay is equal to 588.67 newtons. Excuse me, 588.67 newtons. We plug 5 into equation 3, and we get that AC is equal to 0. We plug 5 into equation 4, and we get that the moment, the reactive moment at point A about the x-axis is equal to negative 784.8 Newton meters. And then the moment about C, which we never really made an equation for that, is equal to 0, and it is equal to the reactive moment of C. Remember, it's always as if I was looking from the positive C, and assuming counterclockwise is positive. I know I repeat myself a lot. Plus 0.8571t times 1. 0.8571t times 1. That is the x component of t. So is this force right here, and it's trying to turn it clockwise, right? So it's trying to turn it. So then we have minus 0.4286t, which is the y component of the force, which is also trying to turn it about the z-axis, and that is times 3 because that's the distance with the y. Okay, so hold on, 0.4286t. Okay, so this one is the y, so it's times 3. Perfect. Just double checking my work here, and then times 1 is the x1. Perfect. And those are the ones that are trying to turn it. Now the weight is not trying to turn it about the z-axis because it's parallel to it, and same thing for the z component of t. That's why they're not here. And we already have t, so we could literally like plug it into this to solve for the moment, and we get that that moment is equal to 588.82 Newton meters. So final answer for AX, the reaction at X, the reaction at Y, the reaction at Z is 0. The reactive moment about the x-axis is negative 784.8. The fact that it's negative, it means that it's going on the opposite direction. And the reactive moment at C is 588.82, and it's positive, so it means that our initial assumption was correct. So final answer. If you made it this far, please make sure you go to finalanswer.com. There you're gonna find all the videos I've been working on and 6 ways to support this channel. And make sure you check my merch store by going to store.finalanswer.com.